So we just finished chapter 36, which was geometric optics. And that pretty much dealt with the particle nature of light, the ray approximation, and so forth. But we wish to investigate the wave nature of light as well. And the wave nature of light is needed to actually explain some various phenomena that we see associated with light that can only be explained through the wave nature, such as interference, diffraction, and polarization. This first lecture will focus on interference. Light waves do interfere with each other, much like mechanical waves do, and it really depends on the amplitude of their electromagnetic field vectors. So these electromagnetic field vectors, the amplitudes, can combine if we consider two conditions for this to happen. And that is that the waves must be totally in phase with each other. And for that to be in phase, we say that they are coherent. And they also must have the same wavelength. For that to be true, we say that they are monochromatic. So our two interfering waves must be coherent in phase and monochromatic, have the same wavelength. Here's one way to do that. If we had a light source that was monochromatic and it was impinging on a slit here from the first screen, that would ensure that what came from that slit would be a monochromatic and coherent wave, because everything coming from that slit will be in phase. And then if that were then incident on a second screen, which has two slits, both of those will act as separate sources, but we've already ensured that those two sources will have the same wavelength and the same phase. So we'll have two sources interfering from that point on that have a monochromatic and coherent sources. So light from a monochromatic source is allowed to pass through a narrow slit. This first slit ensures that the light comes from a tiny region of the source and is indeed coherent. The light from the single slit is then passed through two narrow slits, ensuring that we have two sources that are exactly the same. Another way to produce coherent sources is with lasers. It's much more common to use a laser as a coherent source because the laser can produce an intense, coherent, or same phase signal, which is monochromatic, same wavelength, and can do it over a width of several millimeters, hence allowing you to illuminate multiple slits at the same time, giving you an interference pattern that is well defined, well reinforced. But historically, this whole idea of interference with light began with Young's double slit experiment. It gave the wave model some great credibility. It's inconceivable that particles of light could cancel each other. So in the particle model, if you had two particles of light, two photons of light, if they were to collide, you can't imagine that they would actually cancel each other out, that there would be destructive interference. Indeed, you would imagine that they would add energy together, and that's the only way that they could do it. But in the wave model, where you have crests and troughs, well, it's possible that a crest could interfere with a trough, giving you destructive interference and canceling each other out. So the wave allows that to happen. In Young's double slit experiment, we also can use this experiment to help us with a method of measuring the wavelength of the light. We'll see that in just a moment. Here's how it might look. We have a source, S0, acting as our coherent source, impingent upon two other slits, S1 and S2. And at that point, both sources then will be monochromatic and coherent, and then hence we have a diffraction pattern or an interference pattern extending from there where we can see eventually on the screen areas of constructive interference and destructive interference. For constructive interference, the two signals from each slit should pass to such a way that they will constructively interfere when they get to the screen. The central maximum will be constructive interference because the length from each slit to the central maximum will be exactly the same, and hence the monochromatic coherent sources will both have either a crest or both ways will hit at the same point at the central maximum. It's possible if the path difference between the two was one wavelength, then you would have constructive interference again. You would just have one wave traveling one wavelength more, but at that point they'd be totally in phase. So there will be some point on either side of the central maximum where you will have constructive interference, and other points as well when your path lengths are exactly multiples of one wavelength. On the other hand, you could get a dark area if the path of one signal is half a wavelength longer or shorter than the path of the other signal. So as they get to the screen here, you might have a crest interfering with a trough and hence getting destructive interference. A dark fringe will occur at that point, and at any other successive point where the path difference between one wave and the other is a multiple of half wavelengths. So with this kind of construction with Young's double slit experiment, you'll end up with an interference pattern where you have maximums, points of maximum interference, and minimums, points of destructive interference, where the crest and the trough cancel out. Kind of like the difference between the bright side of the force and the dark side of the force. Kind of like that. Here's a way to look at it mathematically and geometrically. If we had a double slit here, and we have the waves traveling from the slit to some point P, they're going to be traveling out. It kind of looks like a triangle in this sense, but this distance to the screen, this distance L, is very, very large, and the distance between these two slits is very, very small, so that really these paths are actually going to be very close to being parallel as they're coming out. So we have these two rays coming out almost parallel, and so the path difference between the two will be this distance delta right here. And if I look at this triangle, which is a right triangle here, more or less, with the distance d between the slits being my hypotenuse of that right triangle, we see that the distance delta is going to be equal to d times the sine of theta, where theta is actually the angle from the middle part of the screen to our point P on the screen. So this triangle here that has theta here is the same as this theta here and the smaller triangle here. We can determine that through geometric constructions here. With a right angle here, we can see that these angles must be complementary, and hence we would have 90 minus theta for this angle here, and then this angle here also has to be then theta. So for constructive interference, the path difference must either be 0 for our central maximum or some integral multiple of the wavelength itself. We must have that this path difference, which is d sine theta, should be equal to m times lambda, where m is some integer multiple. It could be 0 for the central maximum, and then for each successive maximum, 1, 2, and 3 on either side, it could be an integer multiple of the wavelength. M is called the order number. The 0th order corresponds to the central maximum. First order is the first maximum fringe from the central maximum on either side. Second order is the second bright fringe. Third order is the third bright fringe, and so forth and so on. We can also locate the Y position of these bright fringes by looking at the geometry of these triangles. And we would see, at least for small angles, and every time these thetas are going to be really small because the length L is going to be really large, and our position of the fringes on the screen is going to be small in comparison. So this distance Y is going to be equal to L tangent theta. But for small angles, the tangent of theta is approximately equal to the sine of theta, at least in radians. And since we know the sine of theta is equal to m lambda divided by d from our previous expression, we can substitute that in, and we would get that the location of our bright fringe is equal to the wavelength lambda times the distance L to the screen divided by d, which is the distance between the slits, times m, where m is the order number. M is 0, plus or minus 1, plus or minus 2, and so forth. So this would give us the position of the bright fringes on the screen, given that we know the wavelength, the length to the screen, and the distance between the slits. Our assumptions in coming up with this answer is that the distance L to the screen is much bigger than the slit width. That's certainly going to be true. The distance of the slit width is going to be much bigger than the wavelength of the light. That's definitely going to be true. The wavelength of the light might be on the order of nanometers, and the slit width is going to be something measurable. And theta is small, so that the tangent of theta is approximately equal to the sine of theta. Small angle approximation, that's going to be true as long as we have our fringes pretty close to the central maximum. We could also get dark fringes if the path length, dark fringes. For destructive interference, we need the path difference to be an odd half integer, so that our path difference d sine theta for dark fringes is equal to m plus 1/2 times lambda, where m again in this case is a integer. So for the 0 value of this, we would get our first dark fringe on either side. And for the first value of m, or plus or minus 1 value of m, we would get our second dark fringe on either side. For small angles, again, L tangent theta will equal L sine theta. And since we just determined that sine of theta is equal to m plus 1/2 lambda divided by d, substituting this in, we get that the location of our dark fringes on the screen, y, is equal to lambda L divided by d, m plus 1/2, where m is again 0, plus or minus 1, plus or minus 2. These will be the location of all of our dark fringes. Again, the first dark fringe will correspond to m equals 0. Second dark fringe will correspond to m equals plus or minus 1. Third dark fringe will be m equals plus or minus 2. So here's a summary for bright fringes, like the bright side of the force. We have that our location on the screen is equal to lambda L over d times m, m being an integer starting at 0. For dark fringes, location is lambda L over d, m plus 1/2. Again, m equals 0, plus or minus 1, plus or minus 2. All right, that's enough. Note in either case that your difference in two fringes, if you went from one fringe to the next, that length would be equal to lambda L divided by D difference in delta M. Because if you took the difference between fringe 1 and say fringe 2, then you would have this kind of expression. And that's true for either dark fringes or either bright fringes. The same distance will give you the same. And for if it's successive fringes, then this delta M will actually be equal to 1. So we would have that our change between successive fringes, either bright or dark, will be equal to the wavelength times the length to the screen divided by the distance between the slits. Or, reversing this in solving, we get the wavelength of light would equal the distance between the slits, which we can determine before we start our experiment, divided by the length to the screen, which we also determine as part of our experiment, times the change between the difference in length between two successive lines in the fringe pattern, either two successive dark fringes or two successive bright fringes. Measure that distance, we can get the wavelength of the light. How cool is that? We'll know that this path difference is actually really a phase difference. If we can think of waves of light like a sinusoidal wave, one full cycle of a wave corresponds to a 2 pi difference in phase. So a path difference of one wavelength would also correspond to a 2 pi radian difference in phase. One full cycle. So with this in mind, we can say that the path difference, delta, as opposed to a wavelength, would give us a phase difference of an angle phi over the full phase of one wavelength of 2 pi. Hence, we can think of a angle of phase difference, phi, as being equal to 2 pi over lambda times delta, but delta is equal to the slit width, d, times the sine of theta. So this is 2 pi over lambda, d sine theta is our phase difference. We want to plug this into an intensity distribution and see what we get. Considering we have two interfering waves with a phase difference phi. The interfering wave E1 is equal to E naught sine omega t plus phi, and E2 is equal to E naught sine omega t. So exactly the same waves, only with a phase difference equal to phi. We want to superimpose them, and we'll realize that if you add two sine functions, sine A plus sine B, that's equal to 2 sine A plus B divided by 2 cosine A minus B divided by 2. So adding these two together, we would get that the E field, the amplitude, at some point, P, is equal to 2 E naught cosine phi divided by 2, because we have the A minus B factor and omega t's will cancel out, sine omega t plus phi divided by 2. Because we had 2 omega t's divided by 2 gave us an omega t plus phi divided by 2. So that's just employing this trig identity. The intensity is proportional to the amplitude squared. We know that from chapter 34. So the intensity will be proportional to this E amplitude squared, 4 E naught squared, cosine squared, phi over 2, sine squared, omega t plus phi over 2. But the omega t sine function is varying as a function of time. If we square the sine function as a sinusoidal varying as time, the average of that is equal to 1/2, because it's really bounded between 0 and 1 for the square of the sine function. The average is right in between, right in the middle at 1/2. So we would get then that the average intensity would be equal to some maximum intensity cosine squared phi over 2, where the 1/2 and all the other constants are all encompassed into this one constant, I max. Pi is the phase difference, and hence we can see that the intensity is going to vary as the cosine squared of this phase difference. Subbing for the phase difference that we had earlier, we have that the average intensity is equal to I max cosine squared pi times d sine theta over lambda. Or if we use the fact that the sine of theta is approximately equal to tangent of theta, which is equal to y over L, the distance to the screen over the distance, or distance on the screen over the distance to the screen, we can say that our average intensity is I max cosine squared pi d over lambda L times y. If we were to graph it as a function of d sine theta, we would find with each increasing lambda, 2 lambda into this expression for d sine theta, we would get a repeat of the cosine function, and square that, we get an intensity peak at those points. So we have this is showing where our maximums are and our minimums are on our intensity distribution. Or we just equivalently could substitute in for the sine theta as y over L, and we could say that our intensity is equal to I max cosine squared pi d over lambda L times y. Same kind of distribution function. We can also have interference through an ingenious design called Lloyd's mirror. In Lloyd's mirror, you have a mirror and you have one real source and you have a viewing screen. This real source is going to emit a wave towards this point P, but it also will emit a wave that will reflect off this mirror and head back up towards P as if it were coming from a point behind the mirror, from where the image is. So the reflected ray can be treated as a ray from a source, a second source, S prime, that is located behind the mirror, as far behind the mirror as the real source is above it. However, when something reflects off a mirror, you're going to get a pi phase reversal on that reflection. So we can do the same kind of interference analysis from this double slit, if you will, but it's going to reverse all of our maxima and minima equations because we get a phase reversal on this reflected wave. Because of that, we'll get a bright fringes with the same kind of equation that we had with our double slit pattern earlier for dark fringes. We get bright fringes at lambda L over D m plus 1/2, and dark fringes at lambda L over D m. Because of this pi phase reversal is going to reverse the phenomena. It's half a wavelength, if you will, because pi is half a phase of a full cycle, 2 pi, and that gives us another half wavelength, reversing our formulas for the bright and dark fringes. The slit distance d is the distance between our real source and our image source. So if you knew how far the real source was above the mirror, you would multiply that by 2 in order to get your slit distance d. So you assume that the image is as far behind the mirror as the real source is above it. So take that distance above the mirror, multiply it by 2, get your slit distance d between the sources to use in these equations. That concludes the first short lecture on wave phenomena here in chapter 37. We shall now go on to look at diffraction and polarization.